Well, good morning, team. Welcome back. So we did the valence bond method, a little more advanced bonding theory, supposedly advanced than Vesper, but it turns out both of them have flaws, right? So, sometimes the valence bond method works better. Most of the time, the Vesper model works better, especially for organic molecules and things like that. But let's take a look at this valence bond method and let's tweak it a little bit, all right? This is the process of hybridization. You're going to hear this term a lot in organic chemistry. This may be one of the most important videos for you or concepts for success in organic chemistry, along with drawing Lewis structures and Vesper structures, right? That's with three-dimensional shape. But you're going to go to organic. On day one, I would expect you to be able to write down a Lewis structure and look at every central atom and tell me the hybridization of that. All right, so take a second here, write this down, and I will explain it for you. Woo, had to pause there. You ever just have a coughing fit for no apparent reason? You just get that little thing, you're like, what? I had to pause that before I started coughing all over the video. So anyway, so the valence bond method we saw didn't quite predict the proper bonding. A couple molecules, it'll predict the proper bond angles, would be pretty close, but most of them it fails, all right? Well, let's think about why. What we're doing is we're taking non-bonded atomic orbitals of free atoms, the S, the 1s or the 2pz, 2py, 2px, that kind of stuff, slamming them together, overlapping them, you end up with these 90-degree bond angles if you're using p orbitals, etc., right? But we're making an assumption that once you bond these atoms, they're going to retain, the orbitals will retain exactly the same character as the free atomic orbitals. That's a pretty stretchy assumption, if you ask me, right? I'm not an expert, but that seems kind of fishy because you've got free atoms, you've got bonded atoms in a molecule. That's a little bit different of an environment, right? So what we need to do is take into account that situation. Now, later in molecular orbital theory, we're really going to account for it. Here, we're just going to do a little fudgy factor on it, all right? So what we're going to do, we're going to take experimental evidence of known molecular geometries and bond angles. And what we're going to do is we're going to adjust these atomic orbitals to reflect that bonded environment by morphing or altering those atomic orbitals as they come in to bond. And we're going to morph them in such a way so that they match experimental data. Doesn't that seem kind of backwards? Wouldn't it be nicer to have a theory that actually predicted the proper bond angles? Well, welcome to hybridization and valence bond method, right? So it's actually flipping it. We're taking known experimental data and then getting the orbitals to work. So this process of hybridization, we're gonna hit this pretty hard. So let's show you this process of hybridization, what it's all about, and who created it. So 1931, amazing. This is back, Depression era days, at the beginning of the Great Depression. I mean, it's just insane. Linus Pauling, who I actually I met him when I was an undergraduate. It's just crazy. Back in the 80s, he was I think it was in his 90s or something. I remember him walking down the hallway, and it's a big, brilliant, lumbering guy, just and the nicest guy in the world. Just stop, 2 Nobel Prizes, stop and chat with you, just big hands. And I was like, this guy's like a genius. It was so cool. I just saw him walking down next to the lab hallway by himself. So I went up and said hi. It was really cool. So a chance to meet one of the scientific giants was really cool. But anyway, and this is Linus Pauling. He's the electronegativity guy, right? So he proposed, he noticed some issues with what they were using at the time to try to look at bonds and bond angles and whatnot. And the whole bonding issue was kind of new still. And he looked at the data and then proposed this hybridization concept to try to match the experimental data. And this is before Vesper theory was even put together. So it's kind of weird. Hybridization came before Vesper, and we teach it oppositely. And so what he's saying is that these valence orbitals, right, like a 3p or whatever, 3s, whatever it is, in a free atom, right, they are what they are. But when they come together to start to form a bond, they blend together, right? So let's say I have a sulfur atom or nitrogen or carbon. The valence orbitals that are going to be overlapping blend That's called hybridization. So they're going to blend together. So the S and maybe the 3p orbitals, or maybe an S and one of the p's, whatever it is. And we have to see which orbitals they are based on the known geometry. So we know the geometry, we know the answer ahead of time. We'll pick the atomic orbitals to overlap and hybridize, which should give us some hybrid orbitals, right? So let's say I need 3 atomic orbitals for some reason, maybe an S and 2 p's. And I blend them together. When I add them together, what I'm doing is I'm combining their wave functions. You're algebraically adding and subtracting constructive and destructive interference. So you get this set of resultant orbitals called hybrid orbitals that are all identical. And we're going to find out that if I say I take 3 atomic orbitals and hybridize or blend them together, I will get a set of 3, it's always the same number, 3 hybrid orbitals that are all identical. And it turns out they tend to match the electron group geometry of the VSEPR models that we were looking at. Works out pretty nice. There's a lot of overlap between VSEPR theory and hybridization theory. You get the same answers. All right, so let's take a look real quick at, I'm not going to do the wave function, addition and subtraction, I'm not going to do it. I'll show you the result of it, and a quick little table to be able to predict, use the terminology we use in hybridization and how it relates to VSEPR. Let's do it as an example though. Let's take the ammonia. I think we did ammonia in the valence bond method and it didn't work. Remember the bond angles in experiment are about 107 and we predicted 90 using the valence bond method. So let's apply the hybridization and let's tweak the valence bond method by hybridizing these atomic orbitals before we overlap them. So we'll take that nitrogen atom with its 2s, 2py, 2pz, 2px atomic orbitals. So let's hybridize those 4 orbitals to create some hybrid orbitals, which then overlap with those 3 hydrogen atoms. And let's see what we get for that. So this is going to be our thinking process for every example that we do. And then I'll summarize it later. So I want you to think about it first, and then I'll summarize the impact of this. It's almost so easy, we make it too hard, right? So let's take ammonia as an example. When we did that, we saw that the valence bond method predicted 90-degree angles because we had the 2px, 2px, 2py, 2pz orbitals, and then the hydrogens came in, and you had the 90-degree angles between the x, y, and z axes. But we know experiment shows 107 degrees-ish, to 1 degree. That's not the greatest, right? It's in this sort of the ballpark, but not quite, right? So what are we going to do? Here's the thinking process for hybridization. Thank you, Linus Pauling. Let's do the Lewis structure again, right? So that was it. We have the nitrogen with the 3 single bonds to hydrogens and a lone pair. That's 4 electron groups, right? Would you agree? So in VSEPR, that would be tetrahedral electron group geometry. Well, when you look at hybridization, the number of electron groups in the Lewis structure is the number of hybrid orbitals that you need. So in VSEPR theory, an electron group is a hybrid orbital in valence bond method with hybridization. So they're the same thing. So the number of electron groups on the central atom in the Lewis structure must be the number of hybrid orbitals we need. I can't emphasize that enough. That is the foundation of hybridization right here. You look at the Lewis structure, how many electron groups do you have? Boom, that's how many hybrid orbitals you need. Well, when you're combining the wave functions, the number of hybrid orbitals you get is equal to the number of atomic orbitals that you overlap or hybridize. Right? You're adding those wave functions. So if I want 4 hybrid orbitals, that means I need 4 free atomic orbitals. Right? So we take a look at that central atom, in this case nitrogen. Let's look at that nitrogen and look at what its valence orbitals are. And we need 4 of them, right? So nitrogen, of course, is right here. That's in the second, n equals 2, right? So we've got the 2s, and then the 2px, 2py, 2pz. Whoop, up here. So we actually have 4 in the n equals 2 energy level, principal quantum number, right? N equals 2. We have 2s, 2px, 2py, 2pz, because there's 3p orbitals. That would give us 1, 2, 3, 4 atomic orbitals that we could hybridize by combining those wave functions. That will give us 4 equivalent hybrid orbitals that function as electron groups. So the hybridization should match the Lewis structure, which matches the bond angles that we tend to see in experiment. And not perfect, but for most organic type molecules, it works pretty good, especially carbon-based ones. So let me summarize this idea again, and then I'll show you what hybridization is. All right, this is hard to draw on a two-dimensional surface because remember, this is happening in 3 dimensions, okay? So let's take our 4, remember we have 4 electron groups, so we need 4 hybrid orbitals. That comes from 4 atomic orbitals. So that's the 2s for nitrogen, the 2px with a positive and negative lobe, right? 2py, positive, negative lobe, 2pz, positive, negative lobe. Let's combine those wave functions, right? So you get constructive, destructive interference. So if they're in phase, you get constructive interference. If they're out of phase, the red and the blue, you get destructive interference. So this part of the S is going to subtract or reduce the amount of that red. So the amount of red decreases. But the blue of the 2s amplifies the 2p, so you get a bigger bulb. So the resulting hybrid orbital, if I combine that with that, it kind of looks like a p orbital, but the in-phase part got bigger and more bulbous, more spherical, less teardrop like a p, because you got a mix of this S and P character. And then from the destructive interference, you get this little dangly thing here, like your, what's that uvula thing? Uvula. You did not need to see that. Or a little appendix hanging down there. I'm not an anatomy guy. But if we do that for the 2py, right, and the 2pz, right, we're going to end up with 4 equivalent hybrid orbitals that all look exactly the same. They just point at different angles in 3-dimensional space. So you have one pointing straight up, right, in this case the z-axis. Let me, I'm going to pause and get my model set real quick. Hold on. My daughter and son got a hold of my Molly mod set, started making caterpillars. Good luck. Yeah, leave it for me to pull it apart. So let's take these 4 at different angles, right? So we'll combine them. So we're going to get a 2s2p x combination, 2s2py combination, blah, blah, blah. So you're going to get one that kind of points out in the x direction here. One that kind of points out kind of this angle this way. One that's kind of coming at your face. And one that's coming towards me. Right? So you can see that in 3. So it kind of looks like a tetrahedron, right? So I'm using these as these bigger in-phase lobes. The little red ones we tend not to draw because they tend, when we combine these 4 together, those red ones kind of combine together in the middle, so we just don't draw them, right? So if we combine these 4 together, you end up with 4 equivalent looking hybrid orbitals. Well, they're equivalent, not just equivalent looking, they look exactly the same. They're equivalent, pointing at specific angles that happen to be 109.5 degrees, giving you a tetrahedron, or a tetrahedral shape, exactly what you'd predict from Vesper theory. Oh, isn't that nice? That's not what you get when you treat it with just the individual free atomic orbitals. You get 90-degree angles. But when you blend them, right, boom, you get these more bulbous things here. So you end up with a tetrahedron pointing in those regions of space. Right? 4 atomic orbitals gives you 4 hybrid orbitals. Bang! And that's the number of electron groups. So I want to summarize. We could do this for sp, sp2, sp3, sp3d. This is the only time I'm going to draw this. This was a pain in the butt, right? But you get the idea. 4 atomic orbitals gives you 4 equivalent hybrid orbitals oriented in different different ways in 3-dimensional space. And when you overlap them, the little tiny part from the destructive interference, this kind of blends in the center. And again, we don't draw that. All right. So let me summarize what I just did relating Vesper theory to hybrid orbitals. I almost forgot. How do we label these? Because they lose their atomic character. So we can't call it 2s, 2px, 2py, right? And they're all equivalent. So the notation we use for hybrid orbitals is, well, how many parts s, how many parts p, and later we'll get d, right? So what atomic orbitals did we hybridize and blend together? That's going to be how we use the language, right? So we used 1 part s, everybody agree? And 1, 2, 3 parts p. So 1 part, so it's 25% S, 75% P. That's what the characters look like, right? So they're just more bulbous looking P orbitals. So we call that S plus P plus P plus P, or SP3 hybrid orbitals. So we have 4 SP3 hybrid orbitals. That's what we get when we hybridize an S, a PX, PY, PZ. And then we don't use the N value, N equals 1, N equals 2, N equals 3. Those don't exist anymore for the hybrids. They do for the atomic orbitals. But when we draw the hybrid orbitals, we don't do like 2 SP3 or 3 SP3. You just do SP3 or SP2 or SP3D. Let's look at those combinations. All right, do me a favor. I want you to write this table down on your notes. Left it blank, we'll fill it in together. And then what we'll do is we'll look at some specific, I'll show you what's called a hybridization scheme after this, and then we'll start doing a whole bunch of examples on different videos. We'll get a little more complicated. We'll just do ammonia for this one. All right, so do the first column with the number of electron groups, the second, number of hybrid orbitals we would need to represent that. Third, how many atomic orbitals would we need to hybridize to get that number of hybrid orbitals? Fourth, what would be the notation of those hybrid orbitals? And fifth, what's the equivalent Vesper molecular geometry? So we're tying, right, Vesper with hybridization using the valence bond method. And of course, you only have 2, 3, 4, 5, and 6 electron groups. Those are the only options we have, right? So you should probably be able to fill this in on your own, but we'll walk it through it together. But remember the general foundational rule for hybridization. This is it. Remember this. The number of electron groups that you see on a central atom or any atom that you're hybridizing in the Lewis structure is the number of hybrid orbitals you need, right? The hybrid orbitals are where those electrons go, right? From the electron, whether it's 2 electrons in a single bond from a bonding group, 4 electrons from a double bond, 6 electrons from a triple bond, or a lone pair, or even a free radical. Well, the number of atomic orbitals you need to hybridize to get that number of hybrid orbitals is the same. They're all the same. Don't overcomplicate it. You ready? So if I have 2 electron groups on a Lewis structure, that means I need, yes, take it to the bank, 2 hybrid orbitals. Well, if I need 2 hybrid orbitals, how many atomic orbitals would I need to hybridize? 2. Don't overcomplicate it. Chemistry is not as hard as you think. So if I need 2 atomic orbitals, now remember, the ones that go first, think of them with electron configurations, right? S, P, D, F, right? So the S will always go first, then the P, then the D, then the F, right? So we'll always go S, P, D, F. So S, P, D. I guarantee you we're not going to need any Fs. We're not going to deal with anything that has that many. We'll max out in the D. So take all the S's, and there's only one S orbital, right? And once that's done, then we'll take as many p orbitals as we need. There's only 3 p orbitals. And then if we need more than that, we'll go to the D. We won't need any Fs, trust me. So if we do that, if we need 2 atomic orbitals, that would be 1 s and only 1 of the p's. So that would be called sp hybridization, s plus 1p. And the molecular geometry from that, if you have just 2 electron groups, remember they point on opposite sides. That was linear with 180-degree bond angles. Sweet, huh? A lot of review here. So if you can fill out the rest of this table, that would be fantastic. But I will go ahead and blast through it. So if we need if we have 3 electron groups on the Lewis structure, we would need 3 hybrid orbitals. If we have 4 electron groups, right, say like for the ammonia, 3 single bonds and a lone pair, we would need 4 hybrid orbitals for 4 electron groups. If we need 5 electron groups for an expanded octet, we would need 5 hybrid orbitals. And if we have 6 electron groups, major expanded octet, we would need 6. Oh, yes, the numbers are the same. So let's take a look. If we need 3 hybrid orbitals, how many atomic orbitals would we need to hybridize? 3, not 9. 3. What's the square root of 9? If we need 4 hybrid orbitals, we'd need 4 atomic orbitals to hybridize. If we need 5 hybrid orbitals, we'd need to hybridize 5 atomic orbitals. And if we need 6 hybrid orbitals, yes, we would need 3 factorial atomic orbitals to do it. That was for you math people. All right. If you don't know what a factorial is, figure it out. Go Google it. It's one of my favorite things. 3! The little exclamation point. I love that. It was one of my favorite things in math. So if I need 3 atomic orbitals, I'm going to take the S, that's 1, plus 1 of the P's, doesn't matter, could be PX, PY, PZ, they're all equivalent, degenerate, and then another P. So I need 2 of my 3 P's, so that's SP and P, or SP2 hybridizations. Remember, in organic chemistry, day 1, if I drew a Lewis structure, well, I would try to say, here's a molecular formula, draw the Lewis structure, tell me the number of electron groups on it, and then tell me the hybridization of each central atom. You've got 20 seconds. Oh, right? So you'd be able to look at that carbon's sp3 hybridized, that nitrogen's sp2 hybridized, that oxygen's sp3, right? Boom, boom, boom. I expect you to be able to see that real fast. So if we need 4 atomic orbitals to get 4 hybrid orbitals to get 4 electron groups, that would be the S plus P, like a px, plus py, plus pz. That's 4. So that would be sp3. And that was the example I showed just before this for ammonia, where we took the 2s, the 2px, 2py, 2pz, combine those wave functions, hybridize them, blend them to get 4 equivalent hybrid orbitals that point in 3-dimensional space to give you a tetrahedron. If I need an expanded octet of 5, I need 5 atomic orbitals, s plus px plus py plus bz. I'm out of p's! I need a d. Now, whether that's dx squared minus y squared or dy, it doesn't matter. It's just one of the d's. So it's going to be s plus p plus p plus p, or sp3, d. And then, of course, with 6, I need 6 atomic orbitals, s plus px plus py plus pz plus a d plus another d. So that is 1s, 3 p's, and 2 d's. This is critical. Do not overcomplicate it. Of course, if we've got 3 electron groups, remember that's trigonal planar. If you don't remember that, go look at the video on the molecular geometries. If we have 4 electron groups, that electron group geometry, actually, that's not molecular geometry. That's electron group geometry. Just realized that. I got excited, right? These are the basic ones. And then you could have, subtypes of molecular geometries from that. So fix that one up. Whoops. All right, 4 would be tetrahedral, all right? 109.5 degree bond angles. 120 there, 180, 120, 109.5. Of course, you could have subsets of that. So you could have trigonal pyramid, like ammonia would be trigonal pyramid. sp3d, that was the trigonal bipyramid electron group geometry. So put in trigonal bipyramid. And last but not least, 6 electron groups gave you the octahedral. Don't really need that for hybridization, but I just want you to see the connection between VSEPR theory, electron group geometries, and hybridization. Bang! So let me show you this process of hybridization. I showed you as far as combining wave functions and orbitals, but let's just kind of draw it and show you what's called a hybridization scheme. It's a little bit easier, I think. All right, one of my favorite things to do. I love to scheme, hybridization schemes. So this is going to be a simplified look at when I combine all those atomic orbitals and talked about wave functions overlapping, right? The old Jim Carrey. Right? So we've got the Lewis structure. When we're done with the hybridization scheme, it should predict the Lewis structure. It should predict 3 single bonds and a lone pair. All right, so here we go. What we're going to do is pretty much like an electron configuration. Right? Orbital box diagrams. So if you need to review orbital box diagrams, go review that. But instead of just going horizontally, we're going to go vertically, right? And we're only going to do the valence one. So I'm not going to, normally the 1s would be down here, but we're going to don't include the core, just the valence. So we've got the 2s for nitrogen and the 2p, right? So here's nitrogen. So we've got a 2s. And the 2p, the 3 2p's, correct? Now, how many valence electrons does it have? Well, it's in 5a, where you got 1, 2, 3, 4, 5. So nitrogen has 5 valence electrons in that valence shell. Let's put those electrons in there, shall we? Are you ready? Let's do it in blue. So 1, 2. Remember, that pairs up before they do that jump. And then Hund's rule, 3, 4, 5. So we've got 5 valence electrons in the free nitrogen atom. So what we're going to do, and that just shows the energy, right? Kind of like the Alflau process. We're going to do the unhybridized nitrogen atom on the left, or whatever atom you're looking at. And we'll do the hybridized nitrogen atom on the right with the hybridized orbitals. So the non-hybridized orbitals, hybridized orbitals. So this arrow shows the process of hybridization. So we look up at our Lewis structure and go, well, how many electron groups do we have? 4 electron groups, correct? Well, 4 electron groups requires 4 hybrid orbitals. Which is sp3, right? That would require 4 atomic orbitals. So I need the s and all 3 p. So I'm going to circle them all. I need all 4 of them. To get 4 electron groups, I need 4 hybrid orbitals. To get 4 hybrid orbitals, I need to hybridize 4 atomic orbitals. 1, 2, 3, 4. I need them all. You don't have to specify 2px, 2py, 2pz. They're all degenerate. All right, so I'm going to take them all. So if I take 4 atomic orbitals, I'm going to get 4 equivalent hybrid orbitals that are degenerate, the same energy, just pointing in different directions in space. It's 3 parts p and 1 part s. As long as you get them between, I'm okay. But we need to conserve energy, law of conservation of energy. So really, they're going to be up a little closer to the p. We're going to get 4 of them. And these are my sp3 hybrid orbitals. From the hybridization process. I'm going to blend them together. You can't gain or lose electrons, right? So how many electrons did I circle? Well, I used all 4 of them, so 1, 2, 3, 4, 5. So we had 5 electrons in those, valence electrons in those free atomic orbitals. We're going to have 5 electrons in the hybrid orbital. So let's put the 5 in following Hund's rule. So 1, 2, 3, 4. There's Hund's rule. Got to keep them separated. We still have 1 more, so now pair it up wherever you want, right? Doesn't matter. I'll put it here. That's hybridization. Now, what does this predict? All right. If you see 2 electrons in a hybrid orbital, that is a lone pair in your Lewis structure. So that's a filled hybrid orbital. That is going to be a lone pair in your Lewis structure. Hey, how do you like them apples, right? If you see 1 electron in, it wants another one, okay? So that's going to relate to a single bond. I'm going to show you that's called a sigma bond in a little bit here. But if you see a single electron in there, so that predicts 3 single bonds, right? If you have an unpaired electron. So single bond, single bond, single bond. So that is a match, right? Is it always going to work? Not every time. I think in the homework I'd give you a couple situations, resonance, things like that, where it has some issues. But on my exams, that should always match. Your Lewis structure that you draw should match the hybridization. It should predict the Lewis structure. They should match each other. Okay. So that hybridization scheme predicts 1 lone pair and 3 single bonds, which we will define in the next video as sigma bonds, by the way. That's hybridization. We'll do a whole bunch more examples, but that's enough to chew on at this point. We'll do the next video.